Okay, so this is the lecture number 45 on tutorial whatever we learned in this week. There are some problems we are going to solve. So, you see the example 9.1 in this. So, for example, a mold drain is the most suitable drainage system for heavy clay soils. Okay, so, this remember this because the mold drain is the particular or the special kind of drain which will be used to make drains in a heavy clay soils, because it consists of what you call a bullet kind of the tool. So, which goes inside and the bullet makes kind of a round holes, okay, and this is the shaft, right. So, this kind of tool, so this opening, whatever the opening which is taking place, this will not collapse because of the clay soil, and you can easily install the pipes here. Okay. So, that is the specialty of this mold drain. And in the example 2, during land leveling of agricultural land for irrigation drainage purposes, the acceptable deviation in elevation from the design value in meter is 0.015 or 1.5%. So, this you just remember. And example 3, the gridiron pipe drainage system is more economical than the herringbone pipe drainage system because the number of junctions and the double drained area are reduced. So, this we have already discussed. The gridiron, that is a parallel grid system, drainage system is more economical than herringbone, because the herringbone consists of lot of joints, and also this is the problem with the double drainage. So, it because the shape, okay, the shape of drainage. And then, so example 4, so in a subsurface drainage system, the peak discharge through a tile drain under full flow condition is given by Q is equal to 6.715 into 10 power minus 4 into S power 0.5 into n power minus 1. So, this is an equation given where Q is the discharge in meter cube per second, S drain bed slope, and n Manning's roughness coefficient. Okay, size of the main drain. So, find out the size of the main drain, okay, in mm. So, this is the question. So, Q is given, right. So, since it is a subsurface drainage system, so we consider this is a a circular drain pipe, okay, this is circular drain pipe. So, let us see, this is a given Q is equal to 6.715 into 10 power minus 4 into S power 0.5 into n power minus 1. This is the Manning's equation. We know that Q is equal to A into V, where A is area and V in velocity. So, let us put the Manning's equation into this equation, and considering this circular pipe, and we can get an equation equivalent to this form, right, and then you can get the values of n and other values, okay, values of the size of the drain. Okay. Let us see. So, here put the Manning's equation, that is a V equal to 1 by n into r power 2 by 3 into S power 0.5, and so Q is equal to A into V, right. So, A into V, this is V 1 by n r power 2 by 3 into S power 0.5. So, A is so this is the cross sectional area pi by 4 d square, okay, 1 by n. So, this is r is equal to A by P, okay. So, A is pi d square by 4 and P is a perimeter. So, if you remember this, the perimeter, this is the base. So, the perimeter is half circle. So, that is pi d, okay. So, this way you get pi d square by 4 pi d and S power 0.5. Now, simplify this 0.5 by 4 into d square and 1 by n, d square d power 2 by 3 nearby 4 by 4 power 2 by 3 s power 0.5, and finally q is equal to pi by 4 into 4 into 10 power 4 by 2 by 3 d square. So, you have to simplify this, and after simplification you get the equation in this form: pi by 4 power 5 by 3 d square d power 2 by 3 1 by n s power 0.5, and the given equation is q is equal to 0.31 into d power 8 by 3 1 by n s power 0.5. Okay. So, look at the similarities here and remove the terms which are having say like 1 by n gets cancels out. Okay. And what else, s power this cancels out. So, then equate these two, right, and the rest only the parameter is d, and d can be estimated by equating these two equations, and d is equal to 10 centimeter. Okay. All right. So, there is example 5. In a subsurface drainage system, the tile drains are laid with a slope of 0.28%, right, and to carry a peak discharge of 3 liter per second per drain. If the Manning's n is 0.011, the practical diameter of the tile required is. So, given that the slope is 0.28% and discharge 3 liter per second, and n the slope is 0.011, right, and you have this equation by Manning's equation. So, this is the area A, right, 1 by n, and d by 4 2 by 3 from the previous example, okay, and s power 0.5. So, putting the values, q is given meter cube per second and 0.31. Okay. So, d power 8 by 3, and so except d all other parameters are known. So, substituting the other parameters you can get d as 0.097 or 97.46 mm. Okay. So, here is the example 6. The depths from the soil surface to subsurface tile drains, impermeable soil layer, and the highest water table are measured, right, 2.8. So, this is the depth to tile drain, right, from the base, and then impermeable surface, this is impermeable, impervious or impermeable surface, and then and 0.8 is the highest water table. So, we are expecting the water table to be like this. So, this is the highest water table. So, the effective hydraulic head for drainage in meters is. So, what is effective hydraulic head? So, effective hydraulic head, how do you get it? So, that is let us say, so this is 0.8 meter. So, the hydraulic head will be, this is h. So, that simply you can subtract 2.8 minus 0.8, you get h. So, as I said, this is the depth to surface drainage 2.8, water table 0.8. So, effective hydraulic head is 2.8 minus 0.8, that is 2 meter. Okay. So, these are the examples, some of the examples related to your this week's lectures. So, in this examples, so mostly we covered some of the problems given in GATE examination. So, the mainly the knowing the the drainage characteristics will be estimating the drain pipe diameter. Okay. So, that is the one thing, and the other one is the mole drainage. So, what is the mole drainage, and then in the calculations what in drainage calculations what is the percentage error we can commit, that is the one thing, right. And then finally, so the mostly we will be talking about the head which is maintained in the middle, right. So, in the last example, so what is the effective hydraulic head? So, with I think these problems will be enough to cover the last previous this week's lectures, okay. And you can also go through some other problems in the referred textbooks, okay. Thank you so much.